In this section, we're going to be covering the chemistry of alkenes and alkynes, specifically additions to these multiple bonds. We begin with the hydrohalogenation. A hydrohalogenation reaction occurs in multiple steps and is classified as ionic, which means that we're going to have charges en route, those which are positive and negative. This reaction will proceed via a carbocation intermediate and will have Markovnikov addition for a regiochemical outcome. Remember that regiochemistry means the region where chemistry occurs. In other words, where do we put these new atoms? Markovnikov addition has the higher priority group added to the more substituted carbon atom. We will have addition to a carbocation intermediate from the top and bottom face. Remember that a carbocation intermediate has sp2 hybridization, and since it has sp2 hybridization, the carbocation is flat, which means the incoming nucleophile can add to the top or bottom face with equal preference. This means that we'll have a resultant 50-50 distribution to give a mixed stereochemical outcome. So regiochemistry is dictated by Markovnikov addition, and stereochemistry is dictated by top and bottom face of the carbocation being attacked. I've shown the general reaction here. You'll notice that we have Markovnikov addition because X, which is the higher priority group, is added here at the more substituted carbon. The hydrogen atom right here is added to the less substituted carbon here. You'll notice that the alkene, which was here, has been transformed into an alkane, which is here. Now we're going to cover the mechanism so you understand both the regiochemical and stereochemical outcomes. So the steps of a hydrohalogenation are as follows. First, there's addition of the hydrogen atom to the alkene to generate a carbocation. There may be carbocation rearrangement, which you'll see covered later in this section. There is then nucleophilic attack of the halogen anion onto the carbocation. Let's take a look at how this would work with this example here. Remember that reaction chemistry is all about who is the nucleophile and who is the electrophile. In this case, the hydrogen atom is electrophilic, and the reason for that is because of the bond dipole between H and X, where X is more electronegative and hydrogen is more electropositive. That renders the alkene here as the nucleophile in this reaction. Electrons always flow from nucleophile to electrophile, so the 2 electrons in the alkene will go to attack this hydrogen atom. And at that point, the halide atom will move on. We then make this intermediate, the carbocation, like so. Now at this point, we have a decision. We want to place the hydrogen atom to one of the carbons, and we want to place the carbocation on the other. Now both of these carbocations would be equally good because a carbocation wants to be as substituted as possible. Since both of these carbon atoms are tertiary, it doesn't matter where we put it. So I'm going to place the hydrogen atom here and the carbocation here. I'm then going to bring in the chloride anion, which was released from that first step. Remembering that X can be chloride, bromide, and iodide, so this mechanism would hold regardless of the nature of X. This can then attack from the top or the bottom face with equal preference. Allow me to draw both products so we can take a look here. I will first draw the product of the top face attack, like so, where the methyl here is pointed down, and I will draw the product of bottom face attack, like so, with the methyl pointed up, like so. Now at this point, we need to ask ourselves the question, well, does this actually matter? Is this a chiral molecule? And the answer is yes, which means we need to draw both products because this is indeed chiral. At this point, the last thing we should do is give a distribution, and this distribution here would be 50% this and 50% this, because we have attack from the top and bottom face of the nucleophile with equal preference. So to recap, we have the nucleophilic alkene attacking the electrophilic hydrogen atom with release of the halide anion. This generates a carbocation, which can be attacked from the top or the bottom face by that anion. We check and draw both products to ensure that we know what is being produced, and we ask the question, does it matter? The answer is yes here, because stereochemistry is important. Now watch out, because there may be carbocation rearrangement in this reaction. Again, carbocation rearrangements are covered later in this section. Remember that the more substituted the carbon atom, the more stable the carbocation, and that helps you make decisions about where to place the carbocation and if there would be a rearrangement. Now it's your turn to practice by doing a couple example questions. So with both of these questions, I'm being asked to predict the product of the hydrohalogenation reaction. I know I should have Markovnikov addition, and I know that I'm going to have attack from the top and bottom face with equal preference. Let's draw both products here. I know that Markovnikov addition means that I'm going to add the chloride, again, I could use bromide or iodide, to the more substituted carbon atom. I'll show the hydrogen being added here. We'll put the methyl group here, and we'll place the halide here. And I'll draw the other, just for completeness' sake, so you can see both, and we can decide if it is important that we draw both. Again, I'll show the halide up and the methyl down, and I always like to show that hydrogen atom just for good measure. If you don't show it, it's not an incorrect answer, because remember, if a hydrogen's not shown, it's implied, but I always like to show it to track my hydrogens through this process. So we've drawn both products and we ask ourselves the question, okay, is anything here chiral? The answer is no. And so here, the chirality does not matter, and so we don't need to worry about it. You don't need to draw both products. So the chirality does not matter, which means you don't need to draw both. Again, I like to draw both to check, but it's not a big deal in this particular example. Now, the last question here has two alkenes. We have to decide which is going to be more reactive, and that's going to be entirely dictated by where's the best carbocation. The answer would be here. Because I have a more substituted alkene, that means that I have a more stable carbocation, which means this is where the chemistry will occur. With all that being said, we'll leave this alkene alone. You'll notice here that we can't have Markovnikov addition. Both of these are equally substituted. So we will get the addition of a chloride or halide, if we want to be specific, anion here, like so, and a hydrogen atom, we'll show it here as well with these methyl groups here. And we should ask ourselves the question, do we need to redraw this? Is this indeed chiral? The answer is yes, it is. So we'll draw the other product like so, with the methyl pointing up and the halide pointing down, with the methyl like so, and a hydrogen. We give the distribution here, 50%. 50% of this chiral mixture. It didn't matter that I added the halide to the bottom of the alkene versus the top, because they are created equal. And so this gives us a feel for these types of reactions. From hydrohalogenation, you should be able to predict products, know the regiochemical and stereochemical outcome, and draw the mechanism.